Good morning, ladies and gentlemen, and welcome to Fighting for a 5, Episode 5, brought to you by Couch Potato Brand Foods and Beverages. If you're looking to make gains this quarantine, be sure to try carbo loading with Couch Potato Brand's potato-based beverage. All of the carbs, none of the flavor. All right, moving on. So the document number 5 deals with this problem. If you read down here, the question asks, can one conclude that the mean manual dexterity for people who have completed the 6-week program has significantly increased? So we're trying to make an inference about the population, and all we have is a sample. And notice it says we have a random sample. So we literally have one random sample, and we're trying to make an inference about the mean of the population. All right, so these words here sort of imply to us a few things. First of all, we are going to run a hypothesis test dealing with means. So we're not dealing with proportions. We have one random sample, and you'll notice that the table actually has two lists of numbers. So it is this one random sample that is generating both lists of data. And so there's actually a natural way of pairing these lists of data. And so what we're going to do is actually run a matched pairs t-test. All right. And we're not going to run a hypothesis. We're not going to run a confidence interval because we're not asked to estimate an increase or a decrease in dexterity. What we're simply trying to decide is, frankly, flat out, is there an increase in dexterity? And so that's a hypothesis test and not a confidence interval. All right, so getting started, again, the plan here is to run an inference test about the mean manual dexterity for people who have completed this 6-week training program. All right, so moving on to the plan, I'm going to define the parameter of interest to be the true average difference in manual dexterity scale. And I made it clear that I am subtracting any after minus before. So what I've done is I've taken the two lists of data generated from the one random sample, and I've done the after column minus the before column. This can be easily done in your calculator. I just want to show you here. List 1 has the before, list 2 has the after info. And so in list 3, with list 3 highlighted, I'm just going to press second 2, which gives me L2, minus second 1, which gives me list 1. Press enter, and then list 3 is populated with all of the differences after minus before. All right, and I've written that information down here in this column. All right, so to continue, I now have, that's my sample data. Mu of D is the parameter of interest. Okay, the null hypothesis and the alternative hypothesis. I want to make a point here to say, ladies and gentlemen, your hypotheses will always be about the parameter, right? That is the piece of information that we don't know. That's the piece of information we're trying to infer about. We're going to use the sample to make a decision about that parameter, but our hypotheses are always going to be about the parameter. And in a situation like this, we're going to just assume that essentially the mean difference is going to be 0. In other words, we're going to assume that this 6-week training program will not have any overall effect. But the question is asking, is there evidence that there has been a significant increase? All right, since I did after minus before, my alternative hypothesis will be that mu of D is greater than 0, right? We want to see if overall the after values are greater than the before values. If you did before minus after, then your alternative hypothesis would be mu of D is less than 0, and that would be totally fine. All right, moving on, I'm going to let alpha equal 0.05, and this is a matched pairs t-test. Now let's fill in the observed sample statistics, and they're going to be taken simply from this list of differences. So I want to find the average difference, and I want to find the standard deviation of this sample list. All right, I'm going to use my calculator to do that. I'm going to quit out of here. I'm going to go to stat, calc, 1var stats, and I am in list 3. Okay, so X bar D. So the average difference in this sample is 0.375. And the standard deviation of the differences is 0.3671. Notice I used S of X and not sigma X. S of X is a sample number. Sigma X is, well, if these 12 numbers were the entire population, then I'd use sigma X, but of course that's not the case. All right, so what are we looking at? Well, our sample mean difference is positive. Well, that to me seems like there's an increase in dexterity. But of course, we know that this is just a sample, and there is such thing as sampling variability. So we want to see, okay, yeah, the average difference is positive for this sample, but is it significantly positive? Is it significantly greater than 0? And so we're going to go ahead and crunch the numbers and make that decision. Of course, since we're studying means and we don't have a population standard deviation, that's why we are going to use a t-test. And since we are using a t-test, degrees of freedom are definitely required somewhere on your page. In this case, it would be the sample size minus 1, which is 11. All right, let's go to justify. There are 4 things we need to justify. One, a random sample was mentioned. If you don't believe me, go back. It says a random sample. Okay, so random sample mentioned. Now the 10% condition, 12 is of course less than 10% of all people, and that is literally or I should say 10% of, less than 10% of all people who could potentially take this dexterity program. Okay, so we're going to assume that 12 is less than 10% of all of those people. Since we're trying to run a match pair t-test, we have to sort of describe how we're linking or how we're pairing the data. And we're going to pair the before and after scores by the person generating those before and after scores, which is, of course, in this case, very natural. So person A will be, his before program will be matched with his after, person B before with person B's after, so on and so forth. Very obvious. What I've omitted so far is the nearly normal condition. So we're going to check that together. And I'm going to use a normal probability plot. So of course, nearly normal condition, if the sample size were greater than 30, then that is all I would have to say. I would say since n is greater than 30, the nearly normal condition is met. That's not the case here, and so I have to actually check the normal probability plot. All right, so we're going to go to second, stat plot. Go to plot 1, turn it on. Of course, this last option here is your normal probability plot. My data list is L3. Okay, everything looks good. I'm going to quit. Let me just make sure I have nothing in Y1. Okay, good. And I'm going to press zoom 9. And here we have the normal probability plot. It's not perfectly linear. It never will be, but it's fairly linear. And I'm going to use this as evidence as the nearly normal condition being met. But notice the language I'm going to use. So I'm going to say that the normal probability plot of differences, make sure you're clear about what distribution you're looking at. You're looking at the distribution of differences. So the normal probability of plot of differences is nearly linear. Therefore, sample distribution, I should say the samples, like this one sample's distribution of differences is nearly normal. And there we have it. So all four conditions are actually pretty well met. And what does that mean? Well, that means we can go on and say that our sample averages, our sample average differences are distributed using the t-distribution. They're centered, well, they're going to be centered at what we're assuming is true about the population average difference, and that is that it is equal to 0. And the standard error of this sampling distribution is going to be approximated by taking this number, 0.3671, and dividing by radical n. All right, and let's just get what that number is equal to. Oops. 0.3671 divided by radical 12. Enter. And that is 0.106, let's say. Okay, so that is the standard error of the sampling distributions of sample mean differences. Okay, and just a reminder, the observed, so what we've listed is if we were to calculate all the sample mean differences of sample size 12 from this population, this would be the distribution. But we've, of course, observed one of those from this distribution, and that, of course, was 0.375. So this means that our test stat which is t, will be our observed stat minus the mean or the assumed mean divided by the standard error of our sampling distribution. And that is approximately, all right, 0.375 divided by 0.106. Is approximately 3.5386. Okay, and now we're going to calculate our p-value. So you can do this in two possible ways. You can say the probability that x bar d is greater than 0.375. So what's the probability of observing that? Oh, and why did I choose greater than 0.375? Again, that comes back to our alternative hypothesis. The alternative hypothesis is what determines whether you do an upper tail test, a lower tail test, or a two-tail test. Equivalently, you can ask the question, what is the probability that your test stat is greater than 3.5386? These are both the same exact statements. Okay, now let us go ahead and calculate this probability. I'm going to go to stat. Oop, that's not what I'm going to do. I'm going to go to second distribution, and I'm going to then scroll down to TCDF. Oops. TCDF now only takes, of course, T test statistics. So in this case, when I rewrote it as a T distribution, that's kind of required when you're using TCDF. You need to express this in terms of T. That's just one limitation of the calculator. Our lower bound is that test stat, which is 3.5386. Our upper bound is going to be some large number, 99999999999. Okay, and degrees of freedom I said many more 9s than I typed, but that's all right. And our degrees of freedom is 11. Enter, enter, and we get our p-value of 0.0023, if I'm not mistaken. Yeah, 0.0023. All right, so that's the information. And now we're ready to make a decision. But before we do that, I just want to show how you can do all this very quickly by using the calculator functions that are built in. If we go to stat, scroll over to tests, this is a t-test, right? A match pairs t-test. Since we're really just using one list of data and we have one sample, it's run exactly like a regular t-test. We're going to input the data. My null hypothesis is that mu of d is equal to 0. The data list is L3. My alternative hypothesis is that mu is greater than 0. And I'm going to calculate. And notice in this situation, we get our test statistic, we get our p-value, as well as the observed statistics. Boom. All right, let's move on to the summary. Now, I'm going to interpret the p-value here just so you get some exposure to it once again, because I have a feeling that this upcoming AP stat exam is going to be heavy on interpretations. But in general, if you're not asked explicitly to interpret p-value, it is not required. Anyway, so here's the interpretation of a p-value. The first statement is, well, we are making an assumption about this in order to calculate this probability, I should say. And that assumption is like if H null is true. So I'm going to make the statement that if the mean difference is equal to 0, right? And that is, of course, what we have assumed up here in the null hypothesis. So if mu of d equals 0, then the probability of observing, well, what did we observe? We observed a sample difference of 0.375, but then I'm going to add or greater, because that's literally the probability we're calculating. We're calculating the probability that x bar d is greater than or equal to 0.375. And of course, that or greater is determined completely by the alternative hypothesis, okay? So if the mean difference is equal to 0, then the probability of observing a sample difference of 0.375 or greater is 0.0023. So apparently there's less than a 1% chance of observing what we did observe if H null is true. That seems like a very rare situation. So we're going to go on and make a decision. Since our p-value of 0.0023 is less than our alpha value of 0.05, we will reject, in all caps, we will reject H null. We do have evidence to support the claim that the 6-week program improves manual dexterity. All right, now this answers the question being asked. So when you're running a hypothesis test, this second paragraph that I wrote here, or it's really just a sentence, this second sentence or 2 sentences is a requirement. You should always write a sentence referencing the null hypothesis and your decision on the null hypothesis, and then a follow-up sentence referencing the alternative hypothesis with context, okay? Another key thing is to remember, we never prove the alternative hypothesis. We only support it or fail to support it with evidence. Or in other words, we either do have evidence to support or we do not have evidence to support the alternative. Okay, and once again, context. Context, context, context. All right, ladies and gentlemen, that's all for today. I hope you enjoyed the video. I hope you watched the video. Really, that's the my biggest hope is that you watch. All right, folks, take care. Great chatting. Bye.